Hi, this is Team 11 here with the final stages of our project RAMSES, a real-time alerting and monitoring system for epilepsy and seizures. Next slide. A seizure is a form of uncontrolled electrical activity in the brain characterized by excessive synchronous neuronal discharges. Even beyond the large population of people with epilepsy, up to 20% of critically ill patients admitted to the ICU experience non-convulsive seizures. When a patient has seized for longer than 5 minutes or has back-to-back seizures without regaining consciousness, they are considered to be in status epilepticus. Patients who have fallen into this require immediate medical attention, and if not attended to, are at high risk of dying. A study of 170 subjects at Vanderbilt University Medical Center found a 221% increase in mortality rate in clinically ill patients in the ICU that experience non-convulsive seizures. The danger of a non-convulsive seizure is that there are no physical symptoms. Naturally, that's a huge problem. To put it plainly, people could literally be dying, and there would be no physical signs of it happening. Luckily, the past 3 decades have provided a few solutions, though none of them are perfect. Most recently, continuous EEG has been implemented to monitor patients. This is necessary, but on the front end leaves too much to be read manually. Sloppy and inefficient, the most recent tool to attempt to rectify this persist uses binary predictions that yield too many false positives, diminishing accuracy and rendering it ineffective for addressing the real problem, data reduction. For data that must be read on the scale of seconds to minutes, it's imperative to get epileptologists to the parts that matter fast, and that means defenestrating all the normal readings.
That being said, our goal with this project was not to perform seizure detections like PERSIST, but rather to perform data reduction. It turns out that a majority of continuous EEG data that is collected contains non-seizure activity, yet because of the mistrust of PERSIST, epileptologists still parse through all of the data, particularly in search of more nuanced cases that may even be debatable to human readers. To aid the workflow of these clinicians, we propose a system that focuses on identifying non-seizure activity and only notifies a clinician if there is a very high probability that the patient is seizing. In such a system, there are 3 classifications: healthy, uncertain, and seizing. Such a system would help doctors by giving them confidence when skimming through their data and they are not missing anything important. It helps nurses to better attend to their patients in a timely fashion when absolutely necessary. It helps hospitals free up manpower and money to reallocate elsewhere, and ultimately helps patients receive better care. These were the specs that we were aiming for when we started off the project: a latency of about 4 minutes, a seizure sensitivity of 99%, so we can still detect seizures very well, but also the most important one was data reduction of 80%. And we've met 2 of these requirements: a latency of 10 seconds actually, and the data reduction rate of about 80%.
Now, the algorithm that makes this all possible was made by John Bernabe from the Lit Lab, and then modified by us for real-time data processing. So how it works is it retrieves 10-second clips of EEG from our training data set, and then generates a number of signal features. And these features then used to train a machine learning model called a random forest. A random forest is essentially constructed by randomly sampling from the large training set and building it a decision tree, and then repeating the process many times until you have a large ensemble of decision trees. Next slide. Once the model is fully trained, it's then ready for real-time data processing. Just as in the training phase, it will take 10-second clips of EEG and transform them into features. And then from these features, it will identify if there are any artifacts in the signal and then label them as such. Otherwise, it will run that data through the random forest, which then outputs a probability of that EEG clip containing a seizure. And then this probability is then thresholded such that between 20 and 80% is considered unsure. Above that is definitely seizure. Below that is definitely normal. Next slide. So by running this process on our training data, we found that we were able to detect about 80% of seizures while also detecting about 80% of the normal activity. So this is a very strong starting point, but as we mentioned, we are doing some extra work to meet those specs, namely the seizure sensitivity.
All right, so as we've discussed before, the core of the system that we've built is a Python Flask application. The app's main purposes are to serve the web pages that the user sees on the browser and to facilitate the streaming and classification of data on the back end. Given the amount of data we needed to build our system to handle, a big concern was being able to perform both of these tasks without negatively impacting users' experience. Specifically, it was important to make sure a user didn't even need to wait for the server to finish pulling data or performing predictions before they could access a web page. And as a result, we designed a distributed system that handles the task of streaming and classifying data independently and asynchronously of the serving pages. This is represented in the diagram by the fact that the browser is only interacting with the Flask application, which simply accesses our database to provide whatever predictions are readily available. Meanwhile, the task of updating this database is handled separately by this entity called a celery worker. Once the app is officially deployed, it'll be served within UPenn's hospital network, and only people who are logged into the network and behind the firewall will be able to view it. Also, instead of pulling data from my EEG, it'll access raw data that'll be periodically posted to a database in the hospital and use tools and an SDK we're given to be able to, and we've modified it to do real-time data processing and decrypt data and make predictions.
No, the actual UI that we're working with is the culmination of multiple iterations that we've gone through over the course of the past semester and even last semester. And these iterations have come from taking the project to epileptologists and getting their feedback and implementing them. And instead of going through a list of the features that we've added, we're going to take you through a demo of our system working. So what we have here is the homepage of our application. I've loaded in the patient earlier, and we've configured the system now so that it only displays beds that are currently active. So I've loaded in one patient. His name is John Doe. You can sort the patients if there are more than one patient by the density of the concerning epochs that were predicted, the most recent seizure, and by room number. So if we click on this patient, we can now see their predictions over the course of however long that they've been on the bed. You can click on a region of data. You get this raw data viewer that appears. As it's loading, I'll take you through the other features where on the bottom you have these stats that tell you about the total length of the recording, the time since the last seizure, the percentage of concerning epochs in the data, and the median length of a concerning epoch. These were all stats that were suggested to us by our collaborators. Now, the actual raw data viewer, which is shown up here, you can scroll through it. If you click and drag, you can adjust the gain of the data. You can change the length of time that you want to observe over. You can even change the length of time that you want to observe over in the data over here. Now, the other feature that we've added most recently is we've added the feature to be able to add a patient to the database. So if you wanted to add somebody, say Yvette Johnson to bed 65, you would submit. And then when we go back to the home page, Yvette will show up, and once she has actual recordings to display, you'll be able to click on her and see everything. So now I'll go back to our presentation. So to finish up, the future work that we still need to look into is we need to do some validation on this project. And validation is mainly going to consist of us consulting with the physicians that we've built a relationship with up to this point, and having them use the system and compare how long it takes for them to go through the data with RAMSES versus without RAMSES. Once we validated the system and made sure that we can stream data properly without overriding anything in the hospital network and corrupting any files, we will try to deploy the system behind the firewall. There's also a move being made to convert all of the code to Python code, which will make it possible for us to Docker containerize the app, which will make it easier to transport the code to other universities if they would like to implement the system themselves. We're also looking into more interactivity features such that you can confirm whether or not a prediction is correct, and then update the algorithm's performance dynamically. And lastly, the last step that we weren't able to get to this semester is implementing the functionality of being able to notify physicians for when there are definite seizure occurrences, which we'll use an API called Curator that they've been used in the past in the hospital to implement something like this. We'd like to acknowledge